mechanisms and
yeah.
carboxylic acid derivatives.
Exciting stuff.
It is great stuff.
Yeah.
All right, how do you guys feel about that giant flowchart we did? Do you have any lingering questions about it? Was that a useful way of condensing all of the different conversions that I'm going to expect of you into one graphic? You guys know that normally I like to go through one by one, line by line. We would have shown carboxylic acid forming each of those things. We would have shown the acid chloride forming the carboxylic acid and the anhydride and the ester and the amide. And I really could go through and give you specific examples, but it's just taking an R group and putting the R group on. That's the only thing we do. So is it worth it? That's what I would ask you guys. Was this enough to help you? And I know this is a little different than the one I put on the board yesterday. But is this enough to help you understand these are all the different ways I can convert functional groups between each other? These are all the different ways I can do what's called acyl derivation. I can take my acyl group and derivatize it into any of these other carboxylic acid derivatives. Yeah? Okay. Then I actually want to look at a few specific examples when it comes to anhydrides. We can have what are called symmetric anhydrides, and we can have asymmetric anhydrides. So a symmetric anhydride is when R equals R prime. So in these examples, if the carbon group on the left-hand side of the carbonyl, or on the left-hand carbonyl, is identical to the carbon group on the right-hand carbonyl, that's a symmetric anhydride. We saw two ways to form anhydrides. Looking at this image here, first of all, we know that the carboxylic acid can be used to form any of the anhydrides, but also acid chlorides, which are the most reactive derivative, can be reacted to form anhydrides. So, symmetric anhydrides can be made from either combination. You can take a carboxylic acid to a symmetric anhydride. Let me show you guys an example. Let's take benzoic acid. We're going to need two equivalences of it, so we can put this 2x out here if we want to, or we just know that it's going to react with itself. And then we are going to react this with P2O5. Do you guys remember what P2O5 was? It plays a specific role in this reaction. This is a dehydrating reagent. It chemically pulls out H2 and O. It doesn't necessarily absorb water, but it physically grabs onto those extra hydrogens and oxygen. If we think about stoichiometry, that's going to leave us with two PO3s that each have a hydrogen attached to them, so some sort of phosphite compound. That's not, if that helps you, that's good. That's not really what I would pull your attention to. This is just the reagent that helps us grab this. Now, what if I wanted to do this from an acid chloride? Well, because it's symmetric, I'll have an acid chloride that reacts with a carboxylate. My carboxylate needs a negative charge, or I can valence that carboxylate with a counter ion. And because the carboxylate and the acid chloride have the same carbon group on them, when they react, they form the same product. Now, if you're curious about the mechanism for how this acyl substitution works, the carboxylate acts as a nucleophile onto the carbonyl of the acid chloride. And this creates what we call a tetrahedral intermediate. So the carboxylate binds to the carbonyl carbon, but it opens it into this alkoxide. And this alkoxide actually collapses back down into a carbonyl. It needs to kick off a good leaving group, and chloride here acts as that good leaving group. So it simply adds and then eliminates. That's our substitution step. An asymmetric anhydride happens when R does not equal R prime. And we run into complications if we try to use carboxylic acids to make this. I'm just going to abbreviate this as pH for now. So let's say that we want to make this asymmetric anhydride. Now, you know what? Let's just make it even more clear. What I'm trying to do is make a benzoate and a 2-phenyl ethanoate or a 2-phenyl acetate. But let's just make this a little bit more clear, and let's just have a straight carbon chain. In order to make this, if I'm looking at retrosynthesis, the 2 carboxylic acids that I would need to have is benzoic acid plus propanoic acid. You can see that joining those 2 carboxylic acids would give me this asymmetric anhydride. The issue with this reaction, it does form this product, but it also forms benzoic anhydride, and it forms propanoic anhydride. So unless you're interested in getting a mixture of 3 different anhydrides, whose ratios you can't necessarily predict, making an asymmetric anhydride, best done from an acid chloride. So can you guys give me an acid chloride and a carboxylate that react together to give me this benzoic propanoic anhydride? What do you think? Where could I put these carbon groups? So this pH, does it matter which side it goes on? Should the pH be attached to the acid chloride or should it be attached to the carboxylate? So why would it not matter? What you're saying is maybe I could have both. Yeah? I could have benzoyl chloride or I could have benzoate. But then I would need to have propanoate, and over here I would need to have propanoyl chloride. Is there one synthesis that works and one synthesis that doesn't? They're the same, absolutely. Doesn't matter where your carbon groups come from, they're going to work all the same. Okay, any questions on that? What do you think? Those are our asymmetric anhydrides. Okay. Now, we saw on that graphic how all of the different acid derivatives can be formed from carboxylic acid. We saw how a lot of those acid derivatives can work their way up to a less reactive derivative. But the other thing that I want to look through with you guys is the reduction of these carbonyls. I guess maybe I could have said the reduction of the carboxylic acid derivatives. What are all the reducing agents that we remember? LAH, our strongest one. What else? Sodium borohydride, NaBH4. Anything else?
It would be LiAlH4 and then LAH.
So LiAlH4, lithium aluminum hydride, that's LAH. MnO4 is manganate, so that's typically with potassium. KMnO4, which is an oxidizing agent. MnO2 is also an oxidizing agent.
That's what I was
Yep.
remember if it was reaction or oxidation.
There's one other one, and we mentioned it briefly in this unit. Chromium's an oxidizer. We're looking for reducing agents. Sounds like eyeball. No, that's also an oxidizer. Periodic acid is an oxidizer. Dibol. So remember that dibol is diisobutyl aluminum hydride. And this is a one reduction reagent followed by an aqueous workup. And what I want to demonstrate here is how no matter what your reagent is, although I do need to be careful. Yeah. So what I'm putting up here is simply a version of every acid derivative that is attached to a benzene ring. benzoyl chloride, benzoic anhydride, benzoic acid, methyl benzoate, benzamide, and cyanobenzene. No matter what you have, as long as they have the same carbon chain, these all react first with dibol, followed by an aqueous workup to give you what functional group? Anybody? Not an alcohol. No. Good guess, though.
Cane.
Not alkane. No. A 1 electron reduction. All right, I mean like a 1-step reduction. What do we get? First of all, I think we can agree it's going to have a pH attached to it. And this carbon of the carbonyl is going to be there. What do we get? A 1-step reduction. That means replacing whatever this group is with something that is more electronegative. Or sorry, less electronegative. An aldehyde. You take any of these derivatives, reduce it with dibol, and it produces an aldehyde. I want you guys to tell me which of those seems the most surprising to you. The cyanide, the nitrile. Why? Because there's no oxygen. First of all, I can replace the chlorine with hydrogen. I can replace the anhydride, other side, with hydrogen. I can replace the OH with hydrogen, the OCH3 with hydrogen, the NH2 with hydrogen. But the nitrile doesn't even have a carbonyl. So in this mechanism of reducing the nitrile, there's actually an imine that forms, carbon-nitrogen double bond. And then in the aqueous workup, that imine is hydrolyzed, just like we saw yesterday and the day before. The imine is hydrolyzed to a carbonyl. It's that reverse reaction of forming the imine. Okay. Let's talk about reduction with LAH.
So is that just for benzylic carbonyls?
No, sorry. I just wanted to show you that it doesn't matter what the R group is. You could make this cyclohexane. You could make this an octane chain. You could make this whatever you want. So I'm not trying to imply that this only works when it's benzylic. That is a great point. I wanted to clarify.
Because my question also is like, for example, on the second row.
The anhydride.
Yeah, let's say it's a hydride, but it's not symmetric. If you use a dibol, which one do you cut to get to different products?
You'd have a chance of reducing either one. And there are byproducts that form here. HCl is a byproduct. Carboxylic acid is a byproduct. Water is a byproduct. Alcohol is a byproduct. Amine is a byproduct. Amine is a byproduct again. But it's not so interesting what the byproducts are so much as the conversion of that carboxylic acid to an aldehyde group. All right, now let's do something similar and let's look at what happens when we reduce with LAH. I'll remind you guys that LAH doesn't just have one equivalence of hydrogen, it has 4. The reason that this reaction selectively stops at the aldehyde is because the reagent, Diebol, only has one hydrogen to give. One hydrogen donated to the carbonyl in every case. LAH has 4 hydrogens to give. So you can expect that LAH is going to continue reacting. In fact, this aldehyde forms as an intermediate in the reduction of each of these with LAH. But do you know what else reduces with LAH? Aldehydes. So if you have an excess amount of hydrogen to donate and you form this aldehyde as an intermediate, then the aldehyde gets reduced as well. So Caesar, just to clarify, I'm going to do a very similar list of the acid derivatives there. If you wanted to, you could swap out the carbon chains that we see here for the carbon chains that you see there. It would work just as equally. All right. So let's take a cyclohexyl acid chloride. It's not a benzoic acid chloride. Reduce this with LAH, followed by an aqueous workup. This gives us a primary alcohol. Let's take an asymmetric anhydride because this time both of the anhydrides will get reduced. Two different primary alcohols. If this was symmetric, 2 equivalent primary alcohols. We already know what happens with carboxylic acids. Here's a cyclopropyl carboxylic acid. These get reduced. Primary alcohols. Let's reduce an ester. We already know what happens with esters. They get reduced into 2 alcohols. One of them is always a primary alcohol, and the other one depends on what is attached at the ester linkage. Let's take an amide. Now, I actually want to give us a couple of different amides because it's quite interesting how amides function here. Each of these 3 amides, we're going to react first with LAH, then with H3O+, and then we'll show what each of them forms individually. I think your gut intuition should be to say, well, just like the ester, I should get a primary alcohol And instead of a second alcohol, I should get an amine. I'll just cut off the carbonyl carbon and nitrogen bond, and I'll get an alcohol and an amine.
Do you get both?
No. You don't get an alcohol. What do you get? Just an amine. How many carbon chains in the starting material? Just one. Kind of a weird way to say that. How many carbon chains in the product? Just one. So the ester gets cleaved into two different alcohols, but the amide never breaks a carbon-nitrogen bond. You guys okay if I erase this side? All right, I want to give you guys a comparison. These are called lactones and lactams. They're cyclic esters and cyclic amides. Let's look at what happens when we reduce these two different functional groups, where the only difference is the heteroatom in the ring.
Break open.
Which one?
See the oxygen one probably.
Oxygen one, definitely. We actually saw this in our chapter on alcohols. We said that the carbonyl to ester linkage is going to break, and both carbons, just like before, become alcohols. So this is 1, 2, 3, 4 carbons long with an alcohol on either side. 1,4-butane-diol. What happens with the amide? It gets split open into an alcohol and an amine.
So
Why? Why would you think that? What makes you think that based on this? How many alcohols do you see in these reductions?
no.
Nothing. And the only difference between that lactam, the cyclic amide, and these linear amides is that the carbon group that nitrogen is attached to comes back around and attaches to one of these carbons. That's the only difference. So just imagine that there's something there. What happens? The carbonyl leaves. And you get a cyclic amine. That's it. That's all that happens. That's bizarre, isn't it? Super interesting. It can actually be a useful way to synthesize amines. We're not going to spend much time on amines this semester, if any. But amines being bases and nucleophiles, amines can be hard to synthesize the way you want. But if you can make an amide, then you can reduce it down to the amine that you maybe want it to be. Okay, the last one we should consider then is nitriles. What do we get when a nitrile is reduced? Should we get an alcohol? Should we get an amide? Should we get an amine? That's the question. Yeah. Now, I gave you guys an example here where we have a primary amide, secondary amide, and a tertiary amide. That just describes how many bonds to carbon the nitrogen has. And we showed that they form a primary amine, secondary amine, and a tertiary amine. There is no way to describe the substitution of a nitrile. It's only ever primary. So we're only ever going to get a primary amine. Two carbons, acetamide. Two carbons, acetonitrile. Two carbon reduction of acetamide to ethylamine. Two carbon reduction of acetonitrile to ethylamine. Same amine produced, two different derivative starting materials. How cool is that? Great. I realize I've been saying that a lot. Say that in my OChem 1 class too. I'm not trying to get you guys excited. I am just excited. Any questions? Before we move on, I want to look at acyl addition to the derivatives. Now, when doing acyl addition, it is very hard to make sure that only one equivalence of acyl addition is done. So instead, it's just often to see two equivalences of acyl addition. I'll tell you the reason. The first acyl addition leads to a ketone product, which is typically more reactive to acyl addition than the derivative it started from. Which means if you form that ketone intermediate and you still have, let's say, ester product that you're trying to do acyl addition to, it's likely that the remaining organometallics are going to react with the ketone, since it's more reactive, than they would to the ester. So it's very common to just run multiple equivalences. So I think what I'll do here again is demonstrate how a few of them always go to the same product. And a couple of them run quite different. Sorry, just trying to... Yeah, it's not quite common to see it. Okay, if we take the acid chloride, the acid anhydride, symmetric, we're going to skip the carboxylic acid because organometallics cannot exist in the presence of carboxylic acids. And we'll take the ester. It's less common to see this acyl addition done with amides, not that it's impossible, but we'll actually come back and look at what happens with a ketone as well. These are all going to give us the same product, so I'm going to have this kind of flowchart example again. First, let's react this with phenyl grignard. And we'll follow it with an aqueous workup. Now, to be clear, this is going to be an excess amount of phenyl Grignard, or we could say 2 equivalences of phenyl Grignard. The first equivalence attacks the carbonyl, opens the double bond, which then closes again and kicks off a leaving group. And that leaving group will be the chloride, a carboxylate, or an alkoxide. That forms a ketone intermediate. So each of these will come down to this ketone intermediate, which is then also reactive to phenyl Grignard. So we start from our primary carbonyl carbon, primary ester, primary anhydride, primary acid chloride carbon, and we bring it to a tertiary alcohol. We add 2 new carbon-carbon bonds, and we make an alcohol out of it.
What if the anhydride isn't symmetrical? Would it go to, would it preference one side over the other?
Probably. There's almost always a difference in reactivity between 2 different carbonyl groups. So if you had an asymmetric anhydride, I would probably just avoid doing something like this.
Okay.
Yeah. Maybe not the answer you'd want. But you know what you could do is you could hydrolyze the asymmetric anhydride, separate the 2 carboxylic acids that form, and then turn one of them back into an acid chloride and then continue on your way. Longer process, more challenging for sure. Now here's an odd man out. If I take acetonitrile, sorry, not aceto, if I take anitrile, and even if I react this with an excess amount of Grignard, we form an imine anion as an intermediate that can't react with another equivalence. So we generate this intermediate. That intermediate, unlike the ketone intermediates of all of these reactions, that intermediate isn't reactive to another equivalence of Grignard. So then it just goes through the protonation step, the hydrolysis. That's going to form what functional group once it gets protonated? CN double bond. Is it the oxime, the hydrazone, the imine, or the enamine? Our imine, CN double bond. And imines hydrolyze in the presence of aqueous acid. So this is going to hydrolyze from an imine to what? Imines hydrolyze to what functional groups? What did we form imines from? When we first saw them, we took aldehydes and ketones and we made imines. And then we said if we're not careful, imines will hydrolyze back to aldehydes and ketones. So we're making this imine intermediate and then we're hydrolyzing it, which means the product is a ketone. But why doesn't that ketone react like this one does? Because that ketone doesn't form until the acid workup. And by the acid workup, the Grignard is quenched. There is no more reactivity from the Grignard. So this is an interesting property. All of our derivatives except for the carboxylic acid and less commonly the amide, they can react to form us these tertiary alcohols. But the nitrile gives us a ketone. Okay? Now, there are two reactions that I want to dig into more with you guys regarding esters. And one of them is going to be a mechanism that is on your homework for this section and very likely will be on your unit test or final exam. The first one that I want to look at with you guys is saponification. This is where we take an ester and we react it with sodium hydroxide or potassium hydroxide. And we make a carboxylate salt and an alcohol. And I think you can hear this in the word, but this is actually one of the oldest methods for making soap. Soaps are long carbon chains attached to some sort of carboxylic acid group or a carboxylate group. So if we take something like a triglyceride, a fatty acid, and these triglycerides, they have long carbon chains. So I'm saying 14 units of CH2. I just didn't want to draw that 14 times. Would you agree that this triglyceride, a bioorganic compound, is an ester? It's actually a triester. Here's an ester group, here's an ester group, here's an ester group. When hydroxide is introduced, it attacks each of these carbonyl carbons. And I'm just going to do some abbreviations from here. It opens these carbonyl carbons into our tetrahedral intermediates, just like we were kind of seeing before. I'm just going to abbreviate. I hope you guys are okay with that. This intermediate reforms a carbonyl and kicks off the ester linkage. And what that creates is a carboxylic acid intermediate and an alkoxide intermediate. You know, I apologize. I did a really bad job with my carbon chain. I think you guys would agree that this kind of looks like the same carbon is bonding to this oxygen and this oxygen.
Mm-hmm.
And it's not really meant to be. A triglyceride has a structure more like, I can't draw it well anymore. There's another carbon. There's a carbon that bonds to each of these. Not the main point, to be quite honest. More importantly is the reactivity. Now I want you to think about this step right here. A carboxylic acid forms, and I've lost track of my 14 CH2 groups in the molecule, and an alkoxide. Think about pKa. Think about acid-base reactivity. Alkoxides have a pKa, or their alcohols have a pKa around 15. Carboxylic acids, pKa around 5. That is 10 to the 10 times more acidic. So there is definitely an acid-base reaction that's going to happen here. And it's that acid-base reaction that leaves us with our carboxylate salt and an alcohol. And then you just repeat that process 2 more times. So, back in the olden days, hunter-gatherer times maybe, you'd burn some wood, harvest the ash that comes out of it. Specifically, if you take it in some sort of pot and you wash it, you can get that pot ash. And that, the salts that come out of that pot ash actually led to the name potassium and gave us the chemical potassium. Because you get potassium hydroxide left over from some of the combustion reactions of the organic materials. And you take that pot ash, the potassium hydroxide, and you mix it with animal fat. And the animal fat is composed of organic molecules like this. And the potassium hydroxide and the triglycerides react and leave you with those potassium carboxylate salts, which is just soap, a polar end and a non-polar end. And now you have something that you can clean with. So if the apocalypse ever comes, you guys are trained on how to make soap. That's your job, okay? Leave whatever else to anybody else. Not only that, but you can show the electron arrow pushing for it too. Okay, now that's the saponification of esters, and you could get a carboxylic acid after that. But more importantly, we're going to look at the hydrolysis of esters. This is where we see an aqueous acid solution that's added. H2O, H3O plus gives us a carboxylic acid and an alcohol. We're going to dive into this mechanism, but we're also going to dive into the reverse mechanism, which is called Fischer esterification. I prefer to call it acid catalyzed esterification. This is where we take a carboxylic acid and an alcohol, react it with acid, and we get an ester. So it's these mechanisms that we're going to dive into more. Before we get into them, there's just a couple of other reactions with esters that I think are interesting and I want you guys to see. Esterification by alkylation. That means is I'll add an alkyl group rather than an alcohol. Start with the carboxylic acid. First, we need to deprotonate it. So we add something like sodium hydroxide, which turns our carboxylic acid into a carboxylate. Carboxylates are nucleophilic. And then we can introduce an alkyl halide. And our carboxylate substitutes the alkyl halide. So those of you in lab, those of you in my lab missed this experiment. We had to do it virtually. But this ester on the right-hand side is called banana oil. Smells like synthetic bananas, like banana gum and stuff like that, or banana candies, not banana gum. We make banana oil in our lab through Fischer esterification with an alcohol and an acid and a carboxylic acid. But you could run it through alkylation. You could take a carboxylate, react it with an alkyl halide. This works best on primary alkyl halides. And you just run a simple SN2 substitution. Carboxylate bonds to carbon, bromine leaves. And the last reaction I wanted to introduce you to was trans-esterification. This is basically esterification, but instead of starting with a carboxylic acid, you start with an ester. So what I've got there is R on the carbonyl side, R prime on the ester side, and I'm reacting it with R double prime, just to indicate that I've got different carbon chains everywhere we go. And this gives me an OR double prime ester, and it kicks off an R prime alcohol. Trans-esterification is not, in my opinion, it's not so much a useful synthesis step, so much as it's a warning sign. It's something you need to be cautious of. If you do not want to change your ester group from R prime to R double prime, then you better not be reacting an ester in an acid with an alcohol, or else you might swap what your ester actually is. We're going to see this in Unit 5. We're going to look at how some reactions we do with esters, we need to make sure we pick the right alcohol for the reaction. Otherwise, we can risk trans-esterification. You know what? I think actually to highlight this better, we should indicate that this can work as well by more like alkoxide methods as well. Acidic conditions can run trans-esterification. Basic conditions can run trans-esterification. Okay. Let's show the mechanism for this acid-catalyzed esterification reaction. And before we get too far into it, I know you guys in lab have actually seen this a bit. You've had some introduction to this, so don't just give it away, but tell me your intuition. I'm labeling the oxygens here, 1, 2, 3. And I want us to try and predict which of those 3 alcohols, which of those 3 oxygens in the starting materials becomes the oxygen of the ester in the product. Do you have any intuition about what it would be from the get-go? Caesar, you're nodding. You have a... What would your guess be?
The alcohol.
The alcohol oxygen becomes the ester oxygen? Anybody else have a different feeling? He's like, I already did the homework. That's what I found. So as we go through this mechanism, that's what I want you guys to keep your eyes on. Which oxygens are involved in what steps, okay? Now you guys saw the video from yesterday's lecture on the mechanisms. How do you guys want to see this mechanism done? Stepwise, where we name each step, or fully sequentially, where we just connect everything together? Okay, I've got 2 voting for 1, 2 in indifference. Okay, we'll do a full sequential mechanism. And let's talk about H+. I don't want us to use H3O+ in this example because H3O+ is what hydrolyzes. So we can either use H+ and have no conjugate base, or we can use TSOH or ACOH. Do you guys have any preference? TSOH is actually a good choice here because if you don't know, ACOH is acetic acid, which in and of itself might run an esterification reaction. TSOH, tosylic acid, won't.
So ACOH won't work?
It wouldn't be the best. And the reason it wouldn't be the best is because it might run side reactions of its own. Am I in the presence of acids or bases? Is this acidic conditions or basic conditions? Very acidic. So what should my first step be in acidic conditions?
Protonation.
Protonation. Where should I protonate? The carbonyl oxygen or the carbonyl carbon? Carbonyl oxygen. Would you guys agree that I could protonate the carboxyl oxygen or the alcohol oxygen? And in a reaction where things are hot and moving around and happening, all are possible, but only one is actually going to help our mechanism. I have a weak nucleophile, and I need to make my electrophile more electrophilic. That's only going to happen if my carbonyl becomes protonated. So, carbonyl oxygen becomes protonated, takes on that positive charge, balanced by TSO-. My cyclopentyl alcohol, cyclopentanol, can now act as a nucleophile. This is a tetrahedral intermediate. I start with a carbonyl, I end with a carbonyl, but right now, I don't have a carbonyl. I've also missed something. Don't say it, but just raise your hand when you think you know what I've missed. One of you. 2 of you. 2.5 of you. 3 of you. 4 of you. What is it? The H and the positive charge. What do I need to do now? Deprotonate. So my conjugate base deprotonates what was the alcohol and is becoming the ester. What kind of conditions am I in? Acidic conditions. When you get to a point like this and things seem fine, you need to ask yourself, what is the next step going to be? What kind of conditions am I in? I'm in acidic conditions, something needs to get protonated. Okay, first let's take a second. Oxygens 1, 2, and 3. Oxygens 1, 2. Man, you know, after this nucleophilic attack, after this acyl addition, I really can't tell which oxygen is 1 and which oxygen is 2. Can you? They're just 2 alcohols attached to the same carbon. But I sure can tell oxygen 3. Oxygen 3 is looking more and more like the oxygen that will become my ester. Which oxygen here is going to get protonated? If I protonate oxygen 3, I just go back. I need to protonate either 1 or 2. Which one gets protonated? Either one. Good answer. Since they're the same, it doesn't matter. What I have now is a good leaving group, OH2+, something that will leave the molecule readily. If it just leaves, however, it's going to leave a carbocation. Carbocations don't love to form, so if they can avoid it, they will. Recall our acetal synthesis. We created water just like this, and when that water kicked off, our neighboring oxygen shared a lone pair to create a carbonyl. Now, to be fair, we have 2 oxygens that could share their electrons. So I would absolutely accept either one of these forming the carbonyl. In fact, we can argue that both of them are in resonance with forming the carbonyl. But only one of them makes the most sense for our mechanism because it sets us up for our final step. I've just kicked off water. I still have TSO minus, and what else am I missing? A hydrogen where? The newly formed carbonyl still has a hydrogen attached, and now a positive charge. So TSO minus acts as my conjugate base, gives the electrons back to the carbonyl oxygen. Bada bing, bada boom. Yesterday I gave you guys names for every step, so I still would like to do that. Step 1, protonation. Step 2, acyl addition. Step 3, deprotonation. Step 4, nope, not yet.
They don't show the TSO
Elimination.
Not yet. Protonation. What'd you say, Susan?
Didn't show the TSOH at the end, it's not up.
Oh yeah, thank you. I didn't draw the TSOH at the end, our catalyst. Oh, the other acid. I could have absolutely had you guys use. We could have used sulfuric acid. I'm not gonna lie though, I only like drawing sulfuric acid realistically, which means showing the OH bond and then showing the rest of sulfuric acid. It is such a pain in my opinion. It's so long. Isn't it much easier to write TSOH? It is. In reality, those of you in lab this week are doing esterifications again, and you are going to use sulfuric acid. So it is a good acid in practice. It's not my favorite acid on the board. Okay, so in step 4, we protonated. Step 5, this is what you guys were saying. Elimination. And then step 6, deprotonation. Recall our acetal synthesis. Protonation, addition, deprotonation, protonation, elimination, addition, deprotonation. 7 steps. The acetal synthesis had one additional acyl addition step. So the acetal synthesis and the Fischer esterification synthesis, very similar to each other. They differ by just this much. And I promise you that if you can understand this mechanism, you can make predictions about almost any other mechanism. Why does this happen in the first step? Because you're in acidic conditions. And this is a good base. Well, better than this anyways. Why does this attack? Because now I have a stronger electrophile. Why does this deprotonate? Because it's acidic. Okay? Let's show the ester hydrolysis. Sorry, I realized that I never really totally clarified. We proved that it was oxygen 3, the alcohol oxygen, that manages to be the ester oxygen. And oxygens 1 and 2, they get lost in the shuffle. And we're going to see the exact same thing in reverse here. If we call this 1, 2, and 3, we know that the alcohol will be oxygen 1. The alcohol oxygen is the ester oxygen. We can't necessarily say where 1 and 2 are. What is the opposite of deprotonation? Protonation. Which means my first step in the reverse reaction is protonation. Should I protonate the carbonyl or should I protonate the ester? Well, take a look at the reverse. What did you deprotonate in the last step? We deprotonated the carbonyl. So in the reverse reaction, the first step is to protonate the carbonyl. I apologize. I like to have every reagent that I need present throughout the whole thing. And I had my hydronium, I didn't have my water. So at this point, I now have 2 molecules of water. The The second to last step was elimination. What's the opposite of elimination? Addition. Step 5 was elimination to form a carbonyl, so I need to do addition to the carbonyl. So I have an ester, I have a protonated ester, I have this intermediate that has OH2+. I have an ester, I have a protonated ester, I have this intermediate with OH2+. We're following it backwards exactly. What's the opposite of protonation? Deprotonation. Now you guys know I like coming up with funny little names for functional groups. And what we've got in this intermediate is a geminal diol ether. I don't have a name for it, but I think it's cool. I've reformed my acid, H3O+, which tells me I should be protonating in the next step. But where do I protonate? There's 3 oxygens. If we're going reverse, I should protonate the ether. What was the ester? What will be the alcohol? And H2O. What happens next? Elimination. Carbonyl forms. Alcohol gets kicked off. Now, one thing that I've done here, I've kept my carbon chain in the same conformation that the ring was in. That just helps me make sure not to lose any carbons and to keep everything kind of in the same place, just to keep track of everything. What's my last step? Deprotonate that carbonyl. Good work. And now at this point, if I am confident I know how many carbons are in my chain, I can put it into a lower energy conformation. Those are 2 mechanisms that you might need to know for your unit test and your final exam. Fischer esterification and hydrolysis, a forward and backwards reaction. Similar to the acetal formation and the acetal hydrolysis, forward and backwards. In all reality, on the final exam, it's probably going to be either one of these 2 or one of the acetal reactions, plus a mechanism from Unit 5, because these are all so similar. Kind of a fun little story. When I was in OChem 2, I lost a point on one of my midterm exams for not protonating my carbonyl in the first step. And I'll be honest, I just sat at the Starbucks in town and I just went over mechanisms all weekend long. I was just memorizing them. I wasn't even looking for trends. I wasn't even understanding it. I was just repeating what my professor had put on the board. So when I went to her and I said, why did I lose a point on this mechanism? I don't know what I did wrong. It looks really familiar. She said, you're really trying to argue for points back? You had the high score. And I was like, no, I'm not actually. I'm trying to understand. I have the high score and I don't know what I did wrong? That doesn't make any sense. And she said, you didn't protonate in the first step. You're in acidic conditions. The first thing you should always do is protonate something. Never forgot it. And not only that, but it gave me this perspective. I have no idea what's going on. But there is a logical reason for everything that happens. Why is the first step protonation? There's an acid. That's what acids do. They protonate stuff. I do want to take an aside to talk about the acidity of carboxylic acids. I guess actually I also want to talk about their basicity. If we look at an sp3ch carbon, this has a pKa in the 50s and 60s. That is not an acid. It is incredibly hard to take that hydrogen away. If we look at an alcohol's OH, this has a range from about 15 to 18. That's a much better acid, a weak acid for sure. And if we look at carboxylic, or actually, sorry, I want to look at aryl OH groups, or in other words, phenol. We said that the phenol is more acidic than an alcohol because the oxygen takes a lone pair and distributes it in the aromatic ring, delocalizes it. So the aryl alcohol has a pKa around 10, and we saw that depending on whether there are electron withdrawing groups, and if those electron withdrawing groups are orthopara, that can also decrease the acidity. But when we look at carboxylic acid OH groups, these have a pKa around 5. They're much more acidic. On my OChem 1 exam this semester, I gave them a bonus problem to look at, I don't think that's right, to look at citric acid and predict which of them has the lowest pKa. Which of these hydrogens is the most acidic? Sorry, that's not citric acid. Forgot my carbonyl on the left-hand side. Citric acid has 3 carboxylic acid groups and an alcohol. So given this little chart, we can say that the alcohol is the least acidic. Probably has a pKa around 15. The pKa of that alcohol might be lower than the pKa of other alcohols because of its proximity to all of these electronegative atoms. That is induction. We can use Cario to help us predict acidity. The charge, more positive usually means more acidic, more basic, more negative. The atom, something that's more electronegative is more acidic. Something that's less electronegative is more basic. Or in the same family, something that is larger, more polarizable is more acidic. Increased resonance in the base or increased resonance in the acid decreases reactivity. More resonance makes something less reactive. More resonance in the base, weaker base. More resonance in the acid, weaker acid. Induction is that push and pull of electrons. So this oxygen having all of these electronegative atoms around it has inductive pull away. So when that oxygen does take on a negative charge, All of these other atoms are helping to stabilize it. But its pKa is not the lowest. All of these should have pKa's closer to 5. But which of them has the lowest pKa?
All the same.
They're not all the same. There is one that selectively deprotonates first. It's definitely not this one. This one I told you is an alcohol. So what is different about this one that gives it the lowest pKa?
So is it an induction thing, like they're all dry, so that means that it's more willing to donate the hydrogen?
I would label it as induction, but not because of these groups, primarily because of its proximity to this group. This carboxylic acid is just one atom away from this alcohol, whereas these carboxylic acids are 2 atoms away. So this has more induction. It has a pKa around 4, maybe a little under 4. And then these other ones, while they are equal to each other and they're quite literally symmetric, once one of them gives away its once one of them gives away its hydrogen, the pKa of the other one changes. So they are equal to each other. You could swap those pKa's, but they don't both give away their hydrogen at the same time. So this has the lowest pKa in the molecule. For one, all of the carboxylic acids have resonance in the base. But that carboxylic acid also has induction. Okay, but what about acidity? We just looked at these 2 mechanisms. No, I'm sorry. What about basicity? We just looked at these 2 mechanisms where we had carboxylic acids and selectively the carbonyl oxygen protonated. So let's imagine both scenarios. Carboxylic acid is introduced to an even stronger acid. In one instance, let's imagine that the carboxyl oxygen becomes protonated. And in the other instance, let's imagine that the carboxylic acid, or the carbonyl oxygen, becomes protonated. We can't really base it on charge because both of the oxygens begin neutral. We can't blame it on atom because they're both oxygens. We need to look for resonance. We can't blame it on induction. Both of the oxygens are equal proximity to other oxygen atoms. And we can't really blame it on orbitals. We can predict that they're both sp2 hybridized oxygens. So we really need to look at resonance to see if there's an explanation for which of these should become protonated first. So remember how to look for resonance? It's common to look for a 3-atom system that contains a charge and a pi bond. So here's a 3-atom system, charge and a pi bond. How can I mitigate that charge, though? I really can't. This oxygen has a full octet. It cannot accept electrons. Not to mention, the only way electrons could flow is from the carbonyl to this oxygen. Keep in mind, that's saying carbon takes the electrons away from oxygen and shares it to this other oxygen. Carbon doesn't own those electrons. Oxygen does. So this has no resonance. This is the only form. But this, on the other hand, a charge, a pi bond, and these 3 atoms, the carboxyl oxygen can donate its lone pair and take on the positive charge. Now, I love introductory chemistry students. When they see a resonance form like that, they say, those aren't different. Those are exactly the same. You could just rotate the molecule. You have a protonated carbonyl and you have a carboxyl group. They're exactly the same. And the argument is, they're not. That positive charge is delocalized across both of them. And this is what happened in our mechanism. We couldn't tell the difference between oxygen 1 and oxygen 2 because after the carbonyl becomes protonated, those two oxygen groups, they're identical to each other. They're in perfect resonance. There's no way to tell where the carbonyl is now because the carbonyl isn't anywhere. So for the same reason that carboxylic acids are good acids, they can resonance stabilize the negative charge. Carbonyl oxygens are also good bases, better bases, because they can delocalize that positive charge. And I think that's pretty cool. Okay. Now, if I could go back and do this all again, I would have spent a little less time reviewing the midterm with you guys and maybe a little less time doing nomenclature and stuff. Because we haven't had a ton of time to do synthesis and apply this to multi-step synthesis. You guys know the game already. You've got to know the reactions. You've got to spend time reviewing. So, I was thinking what we could look at together is one of the synthesis problems that's due on the homework tonight. And that way, you guys are able to kind of get a head start on applying synthesis. But I would really encourage you to not just submit the one that we go over right now, but I would encourage you to try your hand at the second one. So, what? Well, I can't stop you. Have you guys tried these yet?
No, that's the one I left off.
I will tell you that solving these two syntheses uses very much the same principles, but kind of in reverse. They're both two-step syntheses. Form an intermediate. Oh, no, 3 steps. 2 intermediates, 3 arrows to solve both of these. Is there one that you guys would like to look at together? Why? You don't like 7-membered rings or you don't like amines?
I don't know, I just picked.
Fair enough, and I appreciate that. Tell me what we have in our starting material. What functional groups are here? No amine. Okay, an aromatic ring. Yep. Aldehyde, amine. Sorry, aldehyde, amide, aromatic ring. And then the product? An amide. Ring. Let's map our carbons. No carbons lost, no carbons added. then I'm thinking, actually I'm going to map my atoms. I'm going to start at that nitrogen, and I'm going to loop my way around through the aromatic ring and over. And Ralph's right. There's no carbons added or lost. Somehow I need to get that nitrogen to bond with the aldehyde carbon. We have seen reactions between aldehyde carbons and nitrogens. That's how we formed imines, enamines, oximes, hydrazines. But we never saw it with an amide nitrogen. Not to mention, the amide disappears. That carbonyl at 2 is no longer there. So before I make the amide in the product, I need to somehow get rid of the amide in the starting material, or maybe I can do it after. Here's my recommendation. Think about how to form the amide. What have you seen? What ways can we form amides? That would be that one big graphic that I gave you that had all of the acid derivatives and carboxylic acid and showed their connections. How many different ways can we form an amide? Could start with yeah, we could start with the carboxylic acid and use an amine and DCC. We could start with an acid chloride and use 2 equivalences of amine, or we could start with an anhydride and use 2 equivalences of an amine. All right, well, from my starting material, aldehydes can be oxidized to carboxylic acids. It's a little bit more challenging to get that aldehyde to an acid chloride. I'd have to go through a carboxylic acid anyways. So it makes sense for my final step here to be synthesizing the amide from a carboxylic acid and an amine. And here's what that amine has to look like. Just cut the bond between carbon and nitrogen. I have the amine that I need, and I have the amide. I provide DCC. DCC is this reagent, by the way. It's kind of a fun little compound. And at the end, when DCC has run its job, it pulls out H2 and O. So it chemically absorbs that water. Okay, so that's my amide synthesis. What I see now is that I need to get rid of the original amide and somehow get to a carboxylic acid. And I told you guys that this is going to be 3 steps, 2 intermediates.
Okay, here's my guess. Are we going to use LAH and H3O to get rid of the carbonyl by the amide carbonyl?
Okay. It is also going to reduce the aldehyde. Are you okay with that?
Yeah.
Why? With what? No. Chromic acid works great, or potassium permanganate. It's got to be a strong oxidizer. Can't be MnO2, can't be PCC. Okay, so what I want you guys to recognize was the reduction of the amide left us with an amine. That's useful, because if you don't know how to synthesize an amine, you could synthesize an amide. Get the amide to an amine, bring that carbonyl of the aldehyde back to a carboxylic acid, link them together. So what we did was complete reduction followed by selective oxidation. The amine won't be oxidized with chromic acid. And the other synthesis takes advantage of some of this a little bit. It's more like extreme oxidation, selective reduction. All right, guys. Thank you for your time. I've taken you way over. I know that this unit felt squished and rushed, but it is a lot of copy and repeat. If you don't know your functional groups, keep studying them, because that is the best way to figure out what is happening in each reaction. Look for what you have, figure out what you're going to make. All right? Okay. Have a good weekend. Good luck on your unit test. Happy studying, and I'll see you next week.